Class number 9, the 5 F's of wave motion: reflection, refraction, diffraction, and interference. It has been common knowledge way before Hieron of Alexandria in the 1st century that light was reflected from plane surfaces with the same angle it was incident. The very important point he made was that light always takes the shortest path. Any other path would have been a longer one. The locus of the points that keep the path with the same length is an ellipse. Those Arabs of the Emirate of Granada in the 14th century already knew that. And they also knew that Heron's principle worked for sound as well. So they figured that bending the ceiling of the hall into an ellipsoidal shape, every sound coming out of a focal point would converge at the other. This is what is known today as a whispering gallery, and they built one in Granada Alhambra Palace back in 1333. Something that cool would not remain singular, and today we find whispering galleries all around the world. A couple of very famous ones: the New York Grand Central Terminal and one at St. Paul's Cathedral in London. Well, let's get back to physics. It was Pierre de Fermat in 1662 that introduced a change to that of the shortest path, as stated by Hieron of Alexandria. He said it was not the shortest, but the fastest. That modified assertion allowed to explain the refraction of light and sound. This statement involved a novel concept at the time: light must have a finite speed, same as sound, but much greater. Consider this very simple problem. Point A on the sand and point B on the road where you can run twice as fast. What is the fastest way to go from A to B? In other words, which is the path for the shortest time? On one hand, you need to reduce your time in the sand, but on the other, it makes your total path longer. Say V sub S is the speed on the sand and V sub R the one on the road. Then the expression for the total time is the sum of both times, which equals the path on the sand over its velocity and the path on the road over the velocity of the road. All we need to do is find the value of x that makes the derivative of this time equal to 0, right?
This is just another one of those silly maximum-minimum problems we had in calculus.
I know this must be a piece of cake for great minds such as yours, but where were we? Yes. We were finding the value of x that makes the derivative of the total time equal to 0. So, taking the derivative and equating it to 0, let's get rid of the radicals and put it in terms of x over d and v sub r over v sub s. Should I go on, or you're already terrified? Yeah. A simple max-min problem had turned into a 4th degree equation on x over d. However, there's an important piece of information that's hiding in this equation. Let's give up finding x over d and concentrate on what the equation above is telling us. Rearranging. The expressions being circled are the sign of theta 1 and theta 2 respectively. And that is the Snell law for refraction being derived from Fermat's.
Wow!
By the 19th century, this Fermat principle evolved into the variational principle of least action, which became the keystone of Lagrange and Hamilton's classical mechanics.
I'm looking at a lot of blank faces here. Maybe not everyone remembers what a variational principle is.
And of course you do, right? Here's the variational principle of least action. Let T and T be the kinetic energy of the mechanical system at time t, and V and T its potential energy. Then the so-called Lagrangian L in T is defined as the difference between the kinetic and the potential energy. The action S between two times is defined as the integral between T1 and T2 of this Lagrangian. The value of the action S will depend on how the system goes from its initial state at T1 to its final one at T2. And here's the kicker. Nature is such that the path every mechanical system takes is the one that makes S a minimum, or in mathematical terms, the variation of the action must be equal to zero. And this is what is called a variational principle.
A derivative equal to zero does not imply a minimum.
You're right, it doesn't. The state of a mechanical system may have many variables. Some may render minimums while other maximums. That's why they try changing the name to that of a stationary action. But it sounds uncool. The least action principle reduces to that of Fermat's. Light and sound as well were then thought to be particle streams. That was the so-called corpuscular view. It became prevalent since light was accepted to have a speed and not something immediate. When light or sound goes from A to B, if the energy of the set corpuscles remain unchanged regardless of the path, the least action principle becomes Fermat least time. The principle's evolution did not stop there. In 1933, Paul Dirac showed how it could be used in quantum interference calculations, and Richard Feynman applied this principle in quantum electrodynamics. Despite its transcendence, Fermat's principle could not even explain all the phenomena observed at its time. For instance, since at the time light was believed to be a stream of corpuscles, the use of rays to represent light was straightforward. Rays were just corpuscles' trajectories. This was very consistent with sunlight coming through windows. Images like this one, where rays could almost be touched, seem to prove it beyond doubt. However, according to this view, a small pinhole bored at the side of a duct box was expected to produce a bright spot on the opposite side. But instead, what happens is that light spreads all over. Rays seem to bend at the border of the hole. This bending effect is called diffraction. For sound, diffraction was even more obvious. Sound didn't require line of sight to be heard. It could enter a room with solid walls through a window or a door and spread to every corner.
Don't pretend. I know you can hear me.
In 1678, Christian Huygens came up with a different approach. Maybe the ripples in a tank gave him a hint. If light was a wave, then when going through a pinhole, it was just behaving like this. Being waves, then light and sound should be best represented by wavefronts, not by rays. A wavefront is the locus of those points in a wave with the same phase of oscillation. For instance, those are wavefronts. Being this a two-dimensional wave, these are circular wavefronts. Rays become just the direction in which the perturbance propagates, or in other words, the direction in which the wave energy moves. In isotropic and homogeneous media, rays are always perpendicular to the wavefront. Every point in a wavefront would be then a secondary source of waves. These are called secondary waves. The envelope of those secondary waves becomes the new wavefront. This of points in the new wavefront becoming wave sources themselves is known as the Huygens principle, and it also explains reflection and refraction too. Here's reflection again. No matter how well Huygens' wave approach explained the observed behaviors, Newton felt that there were other explanations for color and diffraction effects. Owing to his tremendous stature, the corpuscular view prevailed even after 1807 that the English physicist Thomas Young made his now classic double-slit experiment. Here's the description in an authentic British accent.
A schematic diagram of the experimental setup is shown here. Light was made to pass through a slit SO. The waves emerging from this slit was made to pass through two parallel slits S1 and S2. These two slits served as a pair of coherent light sources because waves emerging from them originate from the same wave front and therefore maintain a constant phase relationship. Thomas Young observed that the light from S1 and S2 produced on the viewing screen a visible pattern of bright and dark parallel bands called fringes.
It would have been impossible, even for Newton coming out of his grave, to explain in terms of corpuscles something this similar to waves in a pond. Huygens' principle alone could not completely explain and much less do any calculation of diffraction patterns. That was until Augustin-Jean Fresnel added the right math to it. The concept that colors were waves of different frequencies is also his. Tuberculosis only allowed him to live 39 years. By the time the scientific community realized his greatness, and the Royal Society of London came up with the Rumford Medal, he was already in his deathbed. Today, it is the Huygens-Fresnel principle. Stories are the best teachers, and here's a good one. More than 80 years after his death, Newton's influence was still so great that his corpuscular view of light remained prevalent even after Thomas Young's double-slit experiment in 1807 that could not be explained. Among those still under his influence was Simeon Denis Poisson, and he was one of the members of the judging committee of a competition to explain the properties of light that the French Academy of Sciences had launched. Fresnel entered this competition by submitting his new wave theory of light. Poisson, who held that position for being quite smart himself, argued that the whole thing was absurd. If light was a wave, then it could show behind any illuminated opaque object, just like ripples on the water when they hit an obstacle. However, the head of the committee, Francois Arago, decided to perform the experiment himself. He molded a 2mm metallic disc to a glass plate with wax. He illuminated it, and guess what? He saw the bright spot on the screen 1 meter behind it. The spot became known as the Poisson-Arago-Fresnel spot, and that was the end of the corpuscular theory of light. Great story, isn't it? One of Fresnel's important contributions was the calculation of the reflection and transmission coefficients. It was known that waves were reflected with the same angle of incidence, and with Snell's law, the direction of the refractive wave could be predicted if the incident angle θ1 and the wave speed quotient of both media was known. But this says nothing about how much of the wave is reflected and refracted. Let's go back to D'Alembert's solution to the wave equation. Assuming normal incidence, for medium 1 the displacement u can be expressed like this, where I is the amplitude of the incident wave and r that of the reflected. For medium 2, there would only be a transmitted wave. Considering sound waves, the acoustic pressure at any point x is the isentropic modulus of the media by the partial derivative of u with respect to x.
And where does that come from?
From class number 4 on traveling waves.
Once again, I must admit Sebastian's right. We discussed all about sound waves in elastic media in class number 4. You may review that on your own later, but now let us follow Fresnel's brilliant reasoning. Since the pressure at both sides of the boundary must be the same, let's equate the pressures. Cleaning that up, from class number 5, we also know that the speed of sound equals the square root of b over ρ, where ρ is the average density of the medium, which is a more familiar term than the isentropic bulk ratio B. In those terms, vibration at the boundary must also be the same, so u sub 1 in 0 equals u sub 2 in 0, and so their time derivatives. Cleaning up, dividing this one into the first equation, we eliminate the transmission wave. And after some boring algebra, we get to an expression that relates the derivative of the reflective wave with that of the incident. Now replacing the expression for r primed into the boundary condition for velocities, and after some boring algebra, we get an expression that, after indefinite integration, results in an expression for the transmitted wave.
Integrals are not my strong suit, but...
You don't have a strong suit. You mean your straitjacket.
Stop it. Let's hear the question.
Wasn't there always a constant involved?
It was a fair question, you see. It is not that when you do indefinite integrals, there must be a constant, but there might be one. In this case, there's no displacement difference between the incident and the transmitted wave that is constant in time at x equals 0. Let's finish this. This is the Fresnel's transmission coefficient for normal incidence. And this would be the Fresnel displacement reflection coefficient for normal incidence. However, reflection coefficient is defined for the acoustic pressure wave, which is negative of that. Many years after Fresnel, when transmission lines for electrical signals became common practice, the use of the impedance concept as well as the letter Z for denoting it was adopted by acoustics. That product, C raw, of the speed of sound by the density began to be called the characteristic impedance of the medium. It is also the ratio of the acoustic pressure amplitude to that of the velocity in a traveling wave. When there are standing waves, these may no longer be in phase, and so it becomes a complex number. Waves in high impedance medium showed high acoustic pressure and small displacement. Liquids and solids had higher impedances than gases. Fresnel coefficients can now be expressed in terms of the impedance of the media. Within the same medium, the power of a wave is proportional to the square of its amplitude. So the ratio of the reflected power to that of the incident, calling it PR, is the square of the reflection coefficient. It can also take this form. Since the reflected plus the transmitted must equal the incident power, the ratio of the transmitted power to the incident must then be p sub r is complement to 1. Some easy algebra and we get the power transmission coefficient in terms of the impedances. It can also be expressed in this other form. Some physics now. Say that the impedance of medium 1 is less than the impedance of medium 2. That's the case when sound goes from the air to a denser and almost incompressible medium like water. At normal atmospheric pressure, water is 77 times denser than air, and the speed of sound is 4.4 as fast. The impedance of water is almost 340 times greater than air. Computing the power reflection coefficient, almost all the energy is reflected. Computing the transmission coefficient, only 1% of the incident energy is transmitted. In other words, sound is attenuated almost 20 dBs. That explains the silence you experience when your head goes underwater. Here's an application of what you have just learned.
Shark!
What?
Anything you want to say to the shark? Do it while his head is out of the water.
Nice try, Teach. But jokes are my thing.
Point taken. We just solved a special case of normal incidence, but Fresnel solved the problem for any angle of incidence theta 1. Here are the real Fresnel equations. How about proving the above for homework?
You see, that one was a really good joke.
Well, here's another good joke for you. Well, it's that time. Time for the quiz. Here the answers will follow the question or problem, but hit pause and try answering it first. Say if it's true or false. Light waves going from point A in the air to point B in the water always take the shortest path. Hit pause and try to figure out the answer. Okay, here's my answer. Light will follow this path, but the shortest path would be this one. As for Matt pointed out, it is not the shortest, but the fastest. Vibrational principles are good for corpuscular view, but not for waves. Here's the answer. Variational principles are good for both, but it transcends the reflection, refraction, and diffraction of light and sound. They have proved good for classical and quantum mechanics and electrodynamics as well. So, diffraction, that of light bending around corners, does not happen for sound waves. Here's the answer. Just remember the example.
Don't pretend. I know you can hear me.
It was Fresnel that suggested that colors were waves of different frequencies? And the answer is yes, it's a true statement. The corpuscular view for sound is consistent with the kinetic molecular theory. The answer is corpuscles and molecules are not even distant relatives. By the time kinetic molecular theory was proposed in the 19th century, no one believed in corpuscles anymore. So, the kind of reflection A is what happens to displacement when sound goes from air to water, and B is what happens when sound goes from water to air. And the answer is, for case A, impedance 1 is that of air and impedance 2 that of water. In case B, is the opposite. Case A, impedance 2 is greater than impedance 1. In case B, also the opposite. The reflection coefficient for A is positive because we chose to call positive the case when the reflective wave was inverted. So the case B being the reflection coefficient negative, the reflective wave must have the same sign as the incidence. It is a true statement. Problem number 1. Here's a room with sound-absorbing walls. Two speakers A and B are playing the same pure tone through holes on the wall as shown. A listener standing at 2.67 meters from the wall, when moving 0.76 away from the center, he or she hears nothing due to interference. Calculate the frequency of the pure tone. Here's a solution. If sound could be seen, it would look like this. For the interference to cancel the sound at the ear, the waves coming from speaker A must be 180 degrees out of phase to the ones from speaker B. That means that the distance from A to the ear, E, must be half the wavelength longer than B to E. In math language, calculating the distance from A to E, we get 2.95 meters after rounding it to the second figure. Now the one from B to E. Twice the difference must be the wavelength, and it comes to 0.54 meters. The speed of sound is 340 meters per second, so being the frequency in hertz the quotient of the speed of sound over the wavelength, we get 630 hertz for the pure tone, which answers the question. In this already familiar interference pattern, the dark lines are hyperbolas. Explain why. And here's the explanation. One of the definitions of the hyperbola is that of being the locus of the points that keep a constant distance difference to a couple of fixed points named the foci. In our case, the foci are the wave sources. The two dark lines near the center are the locus of the points that keep a distance difference of half a wavelength. The outer ones are the locus of the points that keep a distance difference of 3/2 the wavelength. And that's why they are hyperbolas. Problem number 3. Find the relation of the number of dark lines with the wavelength and the distance between the sound sources. In other words, given the wavelength and the distance between the sound sources, D, can you tell how many dark lines will you see? And the solution is, dark lines are the loci where destructive interference happens, or where the path difference delta P equals an odd number of half wavelength. That's lambda over 2. In math language, but delta P must be smaller than or equal to D. leading us to this inequality, which allow us to assert that the number of dark lines is twice the maximum value of n that satisfies it. The bottom example is the case of n being equal to 2. There are 4 dark lines that happen when the wavelength is smaller or equal to 2/3 of d, but stays greater than 2/5, which will allow another 2 lines to appear. And that will start being the case in the middle, corresponding to n equal 3. The case shown at the top is for n equals 6, showing 12 dark lines. Here, the wavelength must be smaller or equal to 2/11 of d, but stays greater than 2/13. That will start showing 14 dark lines. The question has been answered thoroughly, right? The background music is already saying that this will be all for class number 9, in which the nature and history of the 5 Fs have been discussed. The next video class will apply this knowledge to echolocation, ultrasound imagery, sonar earthquakes, diffraction from periodic structures, and more. Subscribe to the channel.